everyone, my name is Likafai. My metric number is 224303. So in order to solve this equation, firstly we have two equations that can be used, which is the first order rate reaction, and secondly is a general equation for rate of change of concentration. So since both of them are the reaction rate, we can make it as one equation, and then we do the algebra until we get this, and then we integrate this so that we can find the AT as the subject, and then we do some algebra, just that we need some algebra, and finally we get this answer. So for this question, we just need to use the equation from the question A, which is the equation of AT. In order to find the reaction rate, we need to differentiate the equation into this. Since this is the equation of AT, thus the derivative of concentration A is the rate of reaction. The A is the concentration of reactant, and K is the rate constant. So in order to find the shape of a graph, we assume that A is 0.05 per second, because this is first rate reaction. So here is the table that we found. Here's the value that we found, and here is the graph that we found. It shows the negative gradient. So we can come to the conclusion that the negative side of the reaction rate means that the reactant is consumed and decreased over time. This is because the reactant is used to proceed with a chemical reaction. The negative slope of the line shows the relationship between concentration A and rate of reaction. The concentration A is higher and the rate of reaction is higher to consume reactant A to proceed with the chemical reaction.
So hello everyone, my name is Panitai, metric number 225027. Today I will be going to explain about the question C, integer calculation. So the question asks us to calculate the integer of the rate law over time from t equals to 0 to t equals to t, where t is a specified time to find the total amount of A that has reacted. So first of all, we are going to form a rate law equation, which is rate equals to Ka, which is whereby the K is the rate constant and the A is the amount of A that has reacted. So this is the first equation. So the second equation is you have to form is the differential rate law equation. So rate equals to negative dA over dt. So now we can see that the first equation is equals to the second equation. So there will be Ka equals to negative dA over dt. Now we are going to move the equation or shift the equation. So there will be dA over A equals to negative K dt. Now we are going to integrate the equation. Yeah, we are going to integrate 1 over A equals to we are going to integrate 1 over A dA from A naught, which is the inertial amount of A that has reacted, to the amount AT, which is the amount of A that has reacted, after the specified time t. Then will be equals to the integration of negative K dt from 0 to t, which is the t is the specified time. So after the integration, the answer will be ln A without the substitute from A naught to AT equals to the negative KT without the substitute from 0 to t. So now we are going, so after the integration, so now we are going to substitute the equation. So the final answer will be ln AT minus ln A naught equals to negative KT, which is the final answer that indicates the integer of the rate law over time from t equals to 0 to t equals to t, where t is a specified time to find the total amount of A that has reacted. That's all from me. Thank you.
Hello everyone, my name is Tan Yong Chuan and my metric number is 223127. I'm from group 11 of Engineering Mathematics 1 mini project. So now I will be going through with you the question D in this project, which is improper integral application. So here is how the question looks like. Evaluate the integral of the concentration of A over an infinite time period to determine the total amount of A that will react over an infinite time. Decide whether it will converge or diverge based on your selected function in subsection A. So the question is specifically asking us to do improper integration on the selected function in subsection A, and based on the value we get, we need to determine either it is convergent or divergent. So the selected function in subsection A looks like this, which is concentration of A at any given time equal to initial concentration A naught times e to the power of negative kt, and the range should be 0 to infinity since time can't be negative. And we start by integrate a naught times e to the power of negative kt, and we'll get a naught times e to the power of negative kt divided by negative k, and we sub t and 0 to this integrated function, and eventually we'll get a naught divided by k minus a naught divided by k times e to the power of kt, and then we sub infinity to the t to find the limit of this integrated function, and we'll get a naught divided by k. To ease the understanding, let's sub a naught equal to 10 mole per liter and rate constant k equal to 0.05 second to the power of negative 1 to this integrated function. So we'll get 10 divided by 0.05, which is 200 mole times second divided by liter. So from here, a conclusion can be made. Since the limit of a naught times e to the power of negative kt, where t approaches infinity, can be evaluated, which is 200 mole times second divided by liter in this case. Therefore, the function in subsection A will converge. That's all. Thank you.
Morning everyone, my name is Jeffrey Chongzhen. My metric number is 255697. So today I'm going to explain about the question about series and sequence. So the question first asking us to assume the rate constant changes with temperature following a Taylor series expansion around a nominal temperature. So for this nominal temperature, I could choose any initial temperature value. Then given the first three coefficients of this expansion, I must express KT as a function of temperature. So first, I found out the general formula for Taylor series expansion. So the Taylor series expansion for function fx around a point A is given by fx is equals to fa plus f prime a times n minus a plus f prime prime a times x minus a big bracket square divided by 2 vectorial. Then the question is asking us about the Taylor series expansion for function kt. So I just convert it to the kt function around the nominal temperature T0. So the Taylor expansion would be kt is equals to kt0 plus k prime t0 times t minus t0 plus k prime prime t0 times t minus t0 big bracket square divided by 2 vectorial. After that, I assume kt equals to ln t and assume t0 equals to 10. Eventually, I get kt is equals to ln 10 because I sub the 10 into the kt equation. So I get kt is equals to ln 10 plus 1 over 10 times t minus 10 plus it's minus 1 over 10 square times t minus 10 big bracket square divided by 2 vectorial. So after I calculate this, eventually I will get the last answer, which is negative 1 over 200t square plus 0.2t plus 1.803. So that's all from me for question 5, which is series, and for question E, series and sequence. Thank you so much.
Hello, my name is ENG3001. My metric number is 225699. In this video, we are going to focus on matrix method. The question asks, consider a system of linear reaction involving three substances A, B, and C with a set of coupled first-order differential equation. Represent this system in matrix form and solve for the concentration vector as a function of time. Let us construct a first-order red matrix K for a chemical kinetic process involving three species with a 3 times 3 square representation. The red equation can be written in the following way: C apostrophe equals to Kc. The sum of terms along a column is always 0, and for reversible reaction, the term of symmetric sides remain diagonal before in direction. In the case of two-step consecutive scheme with the corresponding red matrix K, the matrix equation C apostrophe equals to Kc has a general solution given by this equation, where C apostrophe equals to lambda C. This leads to the matrix eigenvalue problem, lambda C equals to Kc. For the example, we can assume that given specific value of K1 is equal to 1 per minute and K2 is equal to 2 per minute, and the concentration of A is equal to 1 molar, B is equal to 2 molar, and C is equal to 3 molar. And the differential equation can be represented from the reaction. After the calculation of matrix, we can see that the rate of change of concentration with respect to time for substance A is minus molar per minute, for B is minus 3 molar per minute, and C is 4 molar per minute. And let's go for it.